Okay, lesson number 3. The remainder of this chapter looks at inequalities, solving inequalities, either linear inequalities or quadratics. We're going to look at the linear inequalities first. So an inequality just means that there's a range of solutions. It's not that it equals something, it's that it can be greater than, less than, or greater than, equal to, less than, or equal to something. So the speed limit on a highway is 100 kilometers an hour. If a car is breaking the speed limit, that means that the speed at which the car is traveling is S is greater than 100. So things to remember, what the inequality signs stand for. So less than or equal to, greater than or equal to, or not equal to. So linear inequalities in a single variable are things like 4x minus 1 is greater than 7, or 1 minus 2a is less than or equal to 5. Solutions to these can be shown on a number line. Things to remember when we're showing them on a number line is an open circle is used for less than or greater than inequalities. And if it is a closed circle, it is less than or equal to or greater than or equal to. So the equal to closes the circle up. So if we look at class example number 1, if we wanted to solve this inequality algebraically, we would solve this pretty much the same way as we would any linear equation. And that would be the first step, would be to remove the brackets. Okay?
Okay, sister.
And then if I subtract or collect my like terms, I get to this point here. Now I'm going to give you a hint. When you have a negative variable, move it to the other side of the equation. Move the negative variable to the other side of the equation, which would make it positive. So I would get a 2x plus 12. Move the 12 over, it becomes negative. So I now have negative 14 is greater than 2x. Divide by 2. And I get negative 7 is greater than x, or x is less than negative 7. If you don't move that variable over, what you end up with is you get negative 2x on the left-hand side, and greater than negative 14 on the right-hand side, sorry. When I go to solve for this, I have to divide by negative 2. And then I have to remember, when I divide or multiply by a negative number, I have to invert or flip the inequality sign. So I still get x is less than 7, or sorry, this should be a positive 14. I still get that x is less than negative 7, provided I remember this part in here. And this is the most common mistake that's made with the inequalities, is we forget to switch the sign. And we only switch the sign when we multiply or divide by a negative number. So if we can keep our coefficient with the variable positive, we never have to worry about it. Okay? So if I go to check this solution using a test case, that means pick a number that's less than negative 7. So give me a number less than negative 7. What number?
Negative 5.
Negative 5 is not less than negative 7.
I meant negative 8.
Negative 8.
It's Monday.
Okay. So if I put this into the original equation,
I was waiting for someone else to say that.
I get 4 minus 2 times 3 plus negative 8, and this is supposed to be greater than 12. So what's 3 plus negative 8?
-5.
And negative 2 times negative 5?
10.
And what's 4 plus 10?
14.
And is 14 greater than 12? Yes.
No.
Now, if I had solved it using this method in here and I had forgotten to inverse this and I had chosen something like a negative 5, I would have gotten 3 plus negative 5 is negative 2. Negative 2 times negative 2 is 4. 4 plus 4 is 8. And I would have had that 8 is greater than 12, which is false, which means that my test case was not true. If I graph this on a number line, the solution, the negative 7, goes in the middle, and then I populate the rest of my number line. Circle negative 7, but fill the circle, or sorry, we don't fill the circle in because it's not equal to. So circle the negative 7, and I want all values that are less than negative 7. So I take an arrow and I point it to the left. Okay. I think that's a review from grade 9. We did inequalities in grade 9. So now if we look at linear inequalities in two variables. 2x minus 3y is greater than or equal to 6. 4p plus 3q is less than 10. What ends up happening is, if this was just an equal sign, I'd have a linear equation, which when I graphed it would give me a straight line. But because I have an inequality, what ends up happening is I have a straight line, but instead of the solutions being things that are on the line, the solution is either the range below the line or above the line. So again, because we're dealing with inequalities, there's several possible solutions that make the inequality true. It's not like with an equation where if it equals something, there's a very finite number of possible solutions. The boundary line is solid or broken according to the following rule. If it is a less than or equal to or a greater than or equal to, we make the line solid, kind of like a closed circle. If it is just less than or greater than, we make the line a dashed line. So that's kind of like our open circle. So if we had to graph linear inequalities without using technology, without using our calculators, the way that we would go about doing it is you start off by graphing your linear equation. You could use a table of values, or we could use that slope y-intercept form of the equation. Once we have identified what our line would be, we draw the line either using a solid or a broken or a dashed line, depending if it said equal to or not equal to. Once you've done that, you're going to get two halves. What you need to do is you need to figure out which half gets shaded. So you pick a test case. Pick a point that lies not on the line, but off the line in one of the two regions. Test it. If it's true, it means that that test point belongs in the solution regions, and I would shade everything. If it's false, it means that it must belong to the other side. Okay? So let's look at the first one. Y is greater than x. So if we go to graph this, what we're going to do is we're going to graph the line y equals x, but are we going to make it a dashed line or a solid line? A dashed line. Okay. So y equals x. That means an input of 2 gives me an output of 2. Whatever the x value is, the y value is going to be the same. So if x is 5, y is 5. If x is negative 5, y is negative 5. So then I can join my points with a dotted line. then I'm going to pick a test case. So I pick a point that's not on this line, such as, let's pick 3 and 5. So that's what we're going to test. So if I input 5 in for y and 3 in for x, is that statement 5 is greater than 3 true or false? This is true. So because it's true, it means that this point has to be in the solution region. So I would shade everything above it. And to show that shading, it's a series of arrows leading up from my graphed line. Or even just a series of lines. Okay, so if we take a look at B, I want to graph this. So what I want to do is I want to put this into a y equals mx plus b form. So I want to get y by itself. In order to preserve the integrity, because this is a negative 2y, I want to put it onto the other side. So 3x is less than or equal to 2y minus 6. Bring the 6 over, which would make it positive. And then I would divide by 2. So 3 halves x plus 6, or sorry, not plus 6, plus 3. Is less than or equal to y. So this is my slope y-intercept form, so that means I have a slope of 3. Or not a slope of 3, a y-intercept of 3. Not the only one who thinks it's Monday. And then my slope, 3 halves. So rise over run. Up 3 over 2. Or down 3 and left 2. So there's my series of points that I would draw. Would I use a solid line or a dashed line? Solid line. And then I want to pick a test point. Okay? The easiest test point to pick is what? 0 and 0. If it's not on the graph, I couldn't pick it in this one because it was on the graph. That's the easiest one to start with. So I test 0 and 0. And I'm going to test 0 and 0 with my original equation. So 3 times 0 minus 2 times 0 less than or equal to negative 6. This all equals 0. So I end up with the statement 0 is less than or equal to negative 6. Is that true or false?
False.
It's false. Which means this point is not in the solution. So it's not part of the solution. So that means I would shade everything to the other side of that line. So if I look at example 3, graph the following inequality without using a graphing calculator. Y is less than 3/4 x plus 3. So I've got this in slope y-intercept form. So I start off by graphing my y-intercept, which is 3. And then from that y-intercept, I can use the slope to get another point. 3/4, rise over run. So it would be up 3 and over 4, which I can't put on the number line, but I can go the other way. Down 3 and over 4. Would I use a dotted line or a solid line to join this? A dotted line, because it's not equal to. So I use my dashed line to join this together. And then I need to pick a test point. And what test point should I use? 0 and 0. So I'm going to get 0 is less than 3/4 times 0 plus 3. And the nice thing with using 0 is it cancels out anything with a variable. So I end up with the statement 0 is less than 3. Is that true or false? True, which means that this point is in the solution region. So my test point, it belongs in the solution, so I shade everything in that region. Okay. If the boundary line is given in the form of y equals mx plus b, the region above the line would represent anything that is a y is greater than, and that was the previous example. Y is greater than x. This one was y is greater than, so I shade the region above. If it is less than, you shade the region below. But for the amount of time it takes you to use a test point, it's not a bad idea to test that point and just double check. And the simplest test point to choose is the one that goes through the origin. After that, the next ones are anything that would be along the x or the y axis, because either one of the coordinates would be 0, which then just leaves less for me to choose from. So if we look at class example number 4, you're given the line and you're asked to write the equation, the inequality that matches to this line. So the diagram shows the solution region to an inequality. The boundary line has intercepts at -2 and 0 and 0 and 4. So how would I determine the equation of this line? I would use the form y equals mx plus b, because this is a linear equation. Do I know what m is? What does m stand for? Slope. How do I calculate slope? Rise over run. But I don't have a rise and a run. I have coordinates. So how can I use the coordinates to find the rise over run? Which coordinates deal with the rise? The y coordinates. So this becomes the difference in my y coordinates, and the run is the difference in my x coordinates. It doesn't matter which one you let be y2 and y1 as long as you're consistent. So if I started with this point as my y2, I'd get 4 minus 0, and on the bottom, 0 minus -2. So 4 minus 0 is 4. What's 0 minus -2?
2.
And what's 4 divided by 2?
2.
So my slope is 2. My y-intercept is my b value. So where does the graph cross the y-axis? At 4. So my b value would be 4. So my equation would be y equals 2x plus 4. If I put that into my graphing calculator, I will get this line. Now to make it an inequality, I have to put in my less than or my greater than. So what I can do is I can go up to above where it said anything below the line is a less than. Or if I'm not sure and I don't trust it, I can still choose that test case. So I can still test a point. We're going to test 0 and 0 because it's in the solution region. So if I put 0 into this equation, I get 0 on the left-hand side and 2 times 0 plus 4 on the right-hand side. And when I simplify this, 2 times 0 plus 4, 4. So now what I want to do is I want to insert an inequality sign that will make this true. So 0 is what to 4? Less than 4. Because this is a solid line, I need to include the equals. So now I go back. Y is less than or equal to 2x plus 4. Okay, so here are your questions. 3A and C, 4A and C, 7, 8A, 10, and 11.